Okay, section 3.6, calculations with balanced chemical equations. Now, this is perhaps the most standard type of chemical calculation that we do in the whole first year of general chemistry. So here's the idea. We've learned how to balance chemical equations. So 2CO gas, for example, that's carbon monoxide gas, plus O2 gas, that's oxygen gas, forms 2CO2, carbon dioxide gas. Notice it's balanced, right? There are 2 carbons on each side and a total of 4 oxygens. Now notice I wrote in circle moles, and the key to this is thinking of this as moles. One way to interpret this equation is ratios. And the ratios that we would say are that 2 moles of carbon monoxide react with 1 mole of oxygen gas to form 2 moles of carbon dioxide. That's an interpretation of the meaning of that. Meaning that if I take 2 moles of CO and I combine it with 1 mole of O2, so that's a total of 3 moles, right? 2 of one and 1 of the other. We will get 2 moles of carbon dioxide. So notice what happened. The number of moles actually got smaller in this reaction. We went from 3 moles down to 2. How does that happen? Well, remember, carbon monoxide has 1 carbon and 1 oxygen. So if we have 2 of them, I can't draw 2 moles. That would take billions and billions of years to draw 2 moles. But I'll just say, look, just like I could say I have 2 dozen, I'll just write a dozen as 1 picture. 2 moles we'll write as 2 pictures, 2 diagrams. So that's 2 moles of CO, and then 1 mole of O2. Okay? So what happens to get carbon dioxide? One of the oxygens has to come over here to the carbon, and the other one has to come to the other carbon to give us 2 carbon dioxides. So notice that in chemical reactions, the number of moles can change from the reactant side to the product side. In this case, 3 moles goes down to 2. Okay? That's essentially the idea. So now let's be a little bit more mathematical about it. What we could say is that 2 moles of CO react with 1 mole of O2. Now notice I drew that as a ratio. The reason I did that is because we often do mathematical calculations, and proportions or ratios are a very useful way to think about it. For example, if I said, I want to convert inches into feet, I could use the conversion 1 foot is 12 inches. Or I could do 12 inches is 1 foot, right? We're using that as a ratio to represent the conversion. We're going to do the same thing with the moles of substances in the balanced equation. So let's write, this is called a stoichiometric ratio. Let's write a ratio for oxygen and carbon dioxide in this particular chemical equation. Oxygen and carbon dioxide. What would that look like? Okay, well, let's think about it. 1 mole of O2, right? 2 moles of CO2. Where did I get the 1 and the 2? It's implied that there's a 1 there, and it's explicit that there's a 2 there. So we're using those moles as ratios. Now you might have said, wait a minute, I had CO2 divided by O2, and that is correct also. Another way of thinking of it is there's 2 moles of CO2 for every 1 mole of O2. That's perfectly fine. What about the relationship between carbon monoxide, 1 oxygen, so that's CO, and carbon dioxide, O2, CO2? what would the ratios be for that? Well, 2 moles CO divided by 2 moles CO2. Or 2 moles CO2, 2 moles CO. Okay? The one that you'll want to use in your calculations, one of those two choices, depends on the context. Okay? So let's take a look at an example here. Suppose I were to say that there are 3.82 moles of CO react. And then we ask the following question. How many moles of CO2 will get formed? How many moles of CO2 will you get if 3.82 moles of CO react? We're going to use these ratios. And here's what you do. You take the one that you're given. So this is given. And you try to figure out the one that's desired. We're trying to figure that one out. Okay? So I'm going to write down what's given. Sorry, 3.82. .82 moles of CO. And then I want to find moles of CO2. So I'm going to pick the ratio so that if I multiply it by that ratio, oops, sorry. So that if I multiply it by that ratio, I get what I want, what I desire. Moles of CO are gone. And we get moles of CO2. So it turns out to be 3.82, right? 3.82 times 2 over 2 is 3.82. So in other words, if 3.82 moles of CO react, you will get 3.82 moles of CO2. But here's another question. Given this information, so given 3.82 moles of CO react, how many moles of O2 react? That's the next question, right? What would that be? Well, now we would look for the ratio. We want to find O2. Do we have a relationship there? Here's one relationship, CO and O2. That's one right there. So let's do this. 3.82 moles of CO. But notice what happens. If I multiply it by this ratio, that's going to give us moles of CO times moles CO. We don't want that. We want to get rid of the moles CO and have moles of O2. So I'm just going to take the reciprocal of that. I'm just going to flip it over. 1 mole of O2, 2 moles CO. Okay, so it becomes 3.82 over 2. So is that 1.91 moles of O2? So it turns out that if you have 3.82 moles of this reacting, half of it, it'll take half as much of the O2 to react, 1.91 moles, and then you'll get 3.82 moles of CO2 in the end. Okay? Now I do want to point out one more aspect of these calculations. By the way, these are called stoichiometric amounts. So when you have reactants and the amount that react are exactly the same ratio as the ratios you have here, like this is a 1 over here, this is a 2, so it's 1/2. This is half of that, it's half. That's called a stoichiometric ratio. They're matched up perfectly. It is often the case that we want to know masses. So we have one more step to do. And this is just a mole to mass conversion. Okay, that's covered in the earlier section in 3.4, but we use it quite a bit. So here's what we could do. We could say, how many grams of CO react? Okay, that's the first one. Okay, well, here's what we do. 3.82 moles of CO converted to grams. 28.01 grams per mole. Where did I get the 28.01? That number just came out of my head, right? That's the molar mass of CO. Remember, carbon is 12.01 grams per mole. Oxygen is 16 grams per mole. 28.01 grams per mole. So that's where that came from. So 3.82 times 28.01 and you get, what is it? 106.99. I'm going to round that to 107. 107 exactly. 107. Let's round it to 107. 3 sig figs. Okay, but what about the O2? How many grams of O2 would have reacted? So how many grams of O2 would react? Well, O2. So you say, okay, 1.91 moles of it reacted. How much does O2 weigh? 32 grams per mole. Oops, sorry, let me be a little bit more formal about that. How did I get 32? Oxygen is 16.00, but it's O2, so there's two of them. So 1.91 times 32. $61.1. Okay, so there's that number. Now, what about the CO2? How many grams of CO2 will be produced? Well, we know it's 3.82 moles. It's 44.01 grams per mole. How do I know that? Carbon is 12.01. Oxygen is 16. But there's two oxygens, right? So that's 44.01 molar mass. So 3.82 times 44.01, and you get 168. Now, I will point out, if you add these two together and round it to the nearest gram, you get 168 grams. And that makes sense, right? Because what we're doing is we're mixing stoichiometric amounts. So if 107 grams of this reacts, 107 grams of this reacts, and 61 grams of this react, you should get 168 grams of this produced. It's internally consistent. Okay? So that is often what you'll want to be doing, is doing mass calculations. So you find the moles of each substance that you're interested in, and then you use the molar masses to convert those amounts into grams. So you'll have to practice these, lots of practice problems, lots of sample problems, all that sort of stuff. Get good at doing these types of problems.